The engine sitting in your car right now is a masterpiece of controlled inefficiency. Think about that for a second. You fill up your tank, you burn your fuel, and roughly 70% of that energy, 70 cents out of every dollar you spend at the pump, just vanishes. It becomes heat. It becomes noise. It becomes nothing useful. And here's the part that should genuinely bother you. We've known there was a better way since 1928. One man figured it out. He built it. It worked. And the most powerful automotive industry in the world looked at his creation, twice as efficient, half the weight, 80% fewer moving parts, and said, "No thanks." Not because it didn't work. Because it worked too well. This is Engineera, and I spend way too much time thinking about the engineering breakthroughs that never got their moment. If you're someone who loves digging into the mechanical stories that textbooks forgot, the inventions that should have changed everything and somehow didn't, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. So let's go back to Stockholm, 1928. The automotive world was on fire, and not in the free piston sense. Henry Ford had just launched the Model A. Cadillac was sketching out the V16. Every engineer worth his slide rule knew exactly what an engine looked like. Pistons, connecting rods, a crankshaft, a camshaft, valve springs, push rods. Hundreds of precision parts working in perfect mechanical harmony, or at least trying to. The internal combustion engine had been refined for about 50 years, and the basic architecture felt like settled science. Nobody questioned it. Nobody thought to. Then a Swedish turbine specialist named Burger Lungstrom walked into his workshop and essentially asked, "What if we're doing this all wrong?" Now, you might be thinking, okay, every era has its garage inventor claiming to have reinvented the wheel. What made this guy different? Here's what most people don't realize. Lungstrom didn't tinker around the edges. He didn't tweak valve timing or experiment with different fuel mixtures. He looked at the entire mechanical structure of the internal combustion engine, the crankshaft, the connecting rods, the camshaft, the valve train, all of it, and asked a genuinely dangerous question. Why does any of this need to exist? His answer was the free piston engine. And it was, depending on your perspective, either the most elegant engineering solution of the 20th century or the most threatening idea Detroit ever ignored. To really understand why what Lungstrom built was so revolutionary, you need to feel the weight of what conventional engines actually require. By 1928, a typical car engine had around 300 moving parts. The connecting rod bearings alone handled thousands of pounds of force with every single combustion event, forces trying to bend and break them thousands of times per minute. The crankshaft, that massive forged steel spine of the engine, had to be machined to insane tolerances and balanced perfectly, or it would shake itself, and everything around it, into scrap metal. The camshaft, geared precisely to the crankshaft, orchestrated a ballet of valves opening and closing at exactly the right microsecond. Get it wrong by a fraction and the engine eats itself. All of that complexity had a consequence. Efficiency hovered around 25%, which means 3/4 of every drop of fuel you burned did nothing useful. The engineers of 1928 knew this. They accepted it. It was the price of mechanical synchronization. You wanted an engine that worked reliably? You built it the way everyone built it. Lungstrom looked at this and saw something different. He saw unnecessary weight, unnecessary friction, unnecessary failure points. And he asked, what is an engine fundamentally trying to do? Convert the energy in fuel into motion. That's it. Everything else, every bearing, every gear, every precisely machined surface rubbing against another precisely machined surface, was just overhead. Mechanical tax. Energy being consumed by the machine to run the machine. His solution was almost offensively simple in concept. Take two pistons, put them in a cylinder facing each other. No connecting rods, no crankshaft. When fuel combusts between them, they fly apart. The compression building up behind each piston, in secondary cylinders at the outer ends, creates a powerful air spring. That air spring bounces them back together. The air between them compresses so tightly, so rapidly, that it reaches the temperature and pressure needed for auto-ignition. Boom! They fly apart again. And again. And again. 50 times per second. Like a perfectly tuned mechanical heartbeat, except there's nothing mechanical about it. Just physics. Just pressure and heat and the fundamental properties of gases doing what gases do. But here's where the genius really sits. Those pistons weren't just bouncing around producing heat and noise. Every stroke, every violent separation of those two pistons, compressed air in those secondary cylinders. That compressed, high-energy air fed a turbine. The turbine spun a generator, or drove a propeller, or powered whatever the application needed. The pistons themselves never touched anything except the walls of the cylinder they lived in. They generated power through the air they compressed, pure, direct, brutally efficient. The numbers Lungstrom achieved should have stopped the engineering world cold. While Detroit's finest engines in 1928 were achieving around 25% thermal efficiency, meaning they were wasting 75% of their fuel's energy, Lungstrom's free piston engine hit 50%, double the efficiency of the best conventional engines of the era, half the fuel consumption for equivalent power output. In an industry that had spent decades optimizing conventional architecture and was proud of squeezing out a percentage point here or there, this was not an incremental improvement. This was a different category of machine. The power-to-weight ratio told an equally striking story. Without a crankshaft, without a flywheel, without a valve train, the free piston engine weighed roughly 40% less than a conventional engine producing the same power. Look, when the Swedish State Railways tested one of Lungstrom's engines in 1934, they put a unit weighing just 2,200 pounds on the stand. It produced 140 continuous horsepower with peaks hitting 200. A comparable conventional diesel of the period weighed nearly 4,000 pounds. Same power. Nearly twice the weight. And that conventional engine needed far more maintenance, had far more failure points, and burned significantly more fuel to do the same job. Here's what most people don't realize about the compression ratio advantage. In a conventional engine, the piston has to stop at exactly the same point every revolution. It's mechanically chained to the crankshaft. The compression ratio is fixed. Set it too high, and the engine detonates, knocking itself apart. Set it too low, and you're leaving efficiency on the table. Every engineer knows this compromise intimately. It's baked into every engine design decision. You pick your compression ratio, and you live with it forever. Lungstrom's pistons had no such limitation. They compressed until the conditions were chemically perfect for ignition. Then combustion pushed them apart. If the fuel quality changed, if you were running low-grade fuel instead of high-octane, the pistons automatically adjusted. They'd bounce with a slightly shorter stroke to achieve the same compression conditions. Swap to premium fuel, and they'd naturally extend their stroke to extract maximum energy. The engine was self-optimizing in a way that no mechanical system with a fixed crankshaft could ever be. This is where it gets really interesting. That self-optimization wasn't something engineers programmed or designed into the system through clever mechanical linkages. It emerged naturally from the physics. The free pistons found their own equilibrium. They adjusted automatically to whatever conditions they encountered: temperature, altitude, fuel quality, load demand. The engine tuned itself, in 1928, without computers, without sensors, without a single electronic component. So why didn't this technology sweep through Detroit like wildfire? Why didn't General Motors license Lungstrom's patents and spend the 1930s retooling their factories around an engine architecture that was demonstrably superior by almost every measurable metric? The answer is one of the most instructive stories in engineering history. And honestly, it's a story that keeps repeating itself in every industry, in every era, right up to today. When Lungstrom's patents began circulating in American engineering circles, the response was swift. And it wasn't curiosity, it was defensiveness. General Motors Research Division produced an internal memo in 1932 describing the free piston engine as theoretically interesting but practically useless. Ford's engineers were reportedly even less measured. One senior engineer allegedly called it Swedish nonsense that violates fundamental principles of mechanical design. Now, think about that phrase for a moment. Violates fundamental principles. What he meant was, it doesn't look like what we already built. Because the physics worked, the test data was real. The efficiency numbers were documented. The engine wasn't violating fundamental principles. It was exposing the fact that the principles the industry had organized itself around were arbitrary conventions, not physical laws. The criticism that stuck, the one that gave the dismissal a veneer of technical credibility, centered on control and predictability. In a conventional engine, everything is mechanically synchronized. The pistons move in lockstep with the crankshaft. The valves open and close at precisely determined intervals tied to shaft rotation. Engineers could calculate exactly what would happen at every degree of rotation. They could write it down. They could measure it. They could guarantee it. Lungstrom's free piston engine was probabilistic rather than deterministic. The pistons bounced at their natural frequency, which could vary slightly with temperature, with altitude, with load. The combustion timing wasn't set by a mechanical relationship. It emerged from physical conditions. And that terrified engineers who had spent careers perfecting mechanical precision. Here's a relatable way to think about it. Imagine you're a master clockmaker. You've spent your entire career building clocks with intricate gear trains, every tooth meshing with every other tooth in a mathematically defined relationship. You can predict exactly where every hand will be at every second. Then someone comes along and says, here's a clock that works by letting the pendulum find its own natural rhythm based on temperature and gravity. It keeps better time. It lasts longer. It has fewer parts. But you can't tell me exactly what angle the pendulum will be at in 3 seconds. It depends on conditions. To the clockmaker, that feels like chaos. To the pendulum, it's just physics. There was also the question of sound. And this one is stranger than it sounds, pun intended. A conventional engine has a familiar rhythm. A regular cadence that American consumers had grown up associating with mechanical reliability. Lungstrom's engine sounded completely different. The pistons bounced at around 50 cycles per second, producing a high-pitched continuous buzz that one contemporary observer described as a giant angry hornet trapped in a metal box. The exhaust wasn't the familiar put-put of a 4-stroke engine. It was a continuous turbine whine. Market research in the 1930s suggested that American consumers would instinctively distrust any car engine that didn't sound normal. The sound of engineering wasn't about physics, it was about familiarity. And familiarity was something Lungstrom's engine fundamentally couldn't offer. But here's the thing. The most powerful reason Detroit rejected the free piston engine wasn't engineering skepticism. It wasn't consumer psychology. It was industrial momentum. By the late 1920s, American automotive manufacturers had invested hundreds of millions of dollars in tooling, infrastructure, and expertise built entirely around conventional engine architecture. Entire factories dedicated to forging crankshafts. Massive casting operations producing cylinder heads and engine blocks. Precision machining lines turning out camshafts. Supply chains delivering conventional engine components from hundreds of suppliers. Tens of thousands of engineers, machinists, and mechanics who had spent careers developing expertise in conventional engine design, manufacture, and repair. Switching to free piston engines wouldn't just have required building new factories. It would have made the existing infrastructure obsolete overnight. Every crankshaft forge would have been worthless. Every camshaft machining line would have had nothing to do. Every mechanic trained to adjust valve clearances and set ignition timing would have needed to be retrained from scratch. The economic disruption would have been enormous. And unlike the efficiency advantages of Lungstrom's engine, which benefited consumers and the broader economy, this disruption would have landed directly on the balance sheets of companies that had enormous political and economic influence. So let's say this plainly. An engine that was twice as efficient, weighed 40% less, had 80% fewer moving parts, and self-optimized. Its compression ratio was set aside because switching to it would have been expensive and disruptive for established manufacturers. The industry chose its own convenience over demonstrably better technology, and they wrapped that choice in technical skepticism to make it look like engineering judgment. Now, you might be thinking, okay, but surely other people noticed. Surely someone outside Detroit looked at these numbers and said, we need to build this. And here's where the story gets genuinely interesting, because that's exactly what happened, just not in America. The French company Sigma, Société Industrielle Générale de Mécanique Appliquée, licensed Lungstrom's patents in 1938 and began serious development. Sigma's engineers looked at the free piston engine not through the lens of automotive manufacturing inertia, but through the lens of applications where its advantages were simply too large to ignore. And the first application they found was submarines. Think about the engineering constraints of a submarine. Space is an existential limitation. Every cubic inch matters. Every pound of unnecessary weight affects diving depth, maneuverability, and operational capability. Fuel efficiency translates directly to range, and range in a submarine is the difference between mission success and a very bad day at the bottom of the ocean. A conventional submarine diesel drove a mechanical compressor to charge air banks. 2 machines. Hundreds of parts. Significant weight. Sigma's free piston engine compressed air directly. 1 machine doing the work of 2 at half the weight and twice the efficiency. The pistons weren't just generating power. They were the compressor. The compression was the point. The French Navy installed Sigma free piston units in several submarines before the Second World War. When German forces captured French naval facilities in 1940, their engineers examined this technology and were sufficiently impressed that they ordered Sigma to continue development under occupation. The GS-34 free piston compressor, developed in 1942, could charge submarine airbanks to 3,000 psi in half the time of conventional systems while burning 40% less fuel. German U-boat commanders filed maintenance reports describing the units as virtually trouble-free, logging thousands of hours of operation between overhauls. Here's what most people don't realize about that timeline. While American manufacturers were dismissing Lungstrom's work as impractical, European military engineers were using it in some of the most demanding operational conditions imaginable. The bottom of the Atlantic Ocean is not a forgiving environment for experimental technology. These engines weren't running in laboratory conditions. They were running in combat submarines under depth charge attacks, in saltwater environments, under extreme pressure, far from any repair facility. And they worked, reliably, consistently, with minimal maintenance. Sigma's most refined free piston design, the GS-34 production unit introduced in 1950, laid out the specifications that should have made the engineering world take notice. 2 moving assemblies. Opposed pistons. No crankshaft. No connecting rods. No camshaft. No valves. Total parts count, 37. A comparable conventional diesel engine of equivalent power contained over 300 individual parts. The GS-34 produced 50 continuous horsepower with short-term peaks of 75. It weighed 420 pounds complete with turbine and generator. Thermal efficiency reached 45% at a time when contemporary automobile engines were still struggling to consistently break 30%. Maintenance on a GS-34 consisted of changing the oil and cleaning the air filter. There were no valve clearances to adjust, no timing chain to inspect, no bearing clearances to check, no cam followers to examine. French industrial plants used these units as emergency generators well into the 1970s. Some logged over 50,000 hours of continuous operation. To put that in perspective, a modern automotive engine is generally considered to have had a good life if it reaches 200,000 miles, which at highway speeds represents roughly 3,000 to 4,000 hours of operation. These French generators were running for 50,000 hours, with fewer parts than your kitchen blender. The submarine application was compelling, but it was the more ambitious projects that revealed just how far engineers were willing to push the free piston concept when they weren't constrained by Detroit's institutional conservatism. And some of these projects went to places that sound, even now, almost science-fictional. Alan Muntz, a British engineer who had worked alongside Lungstrom, developed a free piston engine for torpedo propulsion in 1943. His reasoning was elegant. Conventional torpedoes used compressed air or electric motors. Compressed air meant limited range and a trail of bubbles that gave away the torpedo's position. Electric motors meant heavy batteries and slow recharge times. Muntz's proposal was radical. Instead of driving a turbine with compressed air, why not expel high-pressure combustion gases directly through a nozzle? No turbine, no propeller, no rotating shaft at all. Just controlled, sequential combustions generating thrust. A jet torpedo in 1943. The British Admiralty tested Muntz's design. The test results were, by the reports that survived the war, genuinely impressive. But the Navy ultimately decided it was too radical for wartime adoption. There's a lesson in that decision. Wartime should, in theory, be the moment when militaries embrace superior technology most aggressively. The stakes are absolute. Yet even under those conditions, the established infrastructure and doctrine around existing torpedo technology created enough institutional resistance to shelve something that worked better. If a world war can't overcome institutional inertia, imagine how hard it is in peacetime commercial manufacturing. The most ambitious free piston project of the era came from a completely unexpected direction. Raúl Pateras Pescara was a Spanish-Argentine engineer with a gift for thinking at a scale most engineers found uncomfortable. He took Lungstrom's fundamental concept and asked, what if we scaled this up? Not just to a larger engine, but to an entirely different configuration. His answer was the Pescara engine, a multiple free piston design that arranged individual free piston cylinders in a star configuration, all feeding compressed combustion gas to a single central turbine. The PP-12, tested in 1948, used 12 free piston cylinders producing 2,000 horsepower. It weighed 4,400 pounds. A conventional radial aircraft engine of similar power weighed roughly the same but produced about half the horsepower. The power-to-weight ratio was, in the language of the era, staggering. But the specification that really set Pescara's engine apart was its fuel flexibility. Pescara claimed, and demonstrated, that his engine could run on essentially any combustible liquid. Gasoline, diesel, kerosene. Crude oil straight from the wellhead without refining. The free pistons automatically adjusted their compression to suit whatever fuel chemistry they encountered. The Argentine government funded development. And this wasn't just patriotic vanity. Argentina had substantial domestic crude oil reserves, but limited refining capacity. An engine that could run on unrefined crude represented a genuinely transformative industrial possibility. Test runs confirmed the claims. The engine ran on crude oil. Crude oil. The stuff that comes out of the ground before anyone has done anything to it. No conventional internal combustion engine built before or since has managed that without either destroying itself or requiring extraordinary fuel conditioning systems. Think about what that fuel flexibility would have meant if this technology had been developed and deployed. The geopolitics of the 20th century would look fundamentally different. The entire economic structure built around petroleum refining, the refineries, the distribution networks, the international commodity markets, the wars fought over access to refined petroleum products, all of it would have been at least partially restructured around an engine architecture that didn't care whether you gave it premium unleaded or what came out of a hole in the ground in Venezuela. Now you might be thinking, okay, so why didn't military applications drive this technology into mainstream use the way jet engines, radar, and computers got pushed into civilian life after the war? And this is where the story takes a turn that says something important not just about the free piston engine specifically, but about how technology adoption actually works. The free piston engine didn't just face one competitor for the role of high-efficiency, low-complexity prime mover. It faced one very specific, very powerful competitor that emerged at exactly the wrong historical moment. The aircraft gas turbine. By the late 1940s and into the 1950s, jet engine technology developed under wartime urgency was rapidly maturing. Pratt & Whitney, Rolls-Royce, General Electric, these companies had spent billions of dollars and employed thousands of the world's best engineers developing gas turbines that were becoming increasingly reliable, increasingly efficient, and increasingly understood. Manufacturing infrastructure existed. Training programs existed. Parts supply chains existed. The gas turbine offered many of the same fundamental advantages as the free piston engine. Fewer moving parts than a piston engine. High power-to-weight ratio, multi-fuel capability, smooth operation without the vibration inherent in reciprocating engines, and crucially, it had the backing of the most powerful military-industrial complex in history. When the United States military was spending on gas turbine development, it wasn't spending on free piston development. The engineering talent was flowing one direction. The infrastructure was being built for one technology. And when a choice had to be made between an established, funded, understood technology with known failure modes and an unconventional technology with spectacular test results, but limited institutional support, the established technology won. For automotive applications specifically, the free piston engine faced a challenge that its proponents hadn't fully anticipated. In the 1960s, as American emission standards began to emerge and tighten, engineers working on conventional engines discovered something important. Electronic controls could be used to precisely manage fuel delivery, ignition timing, and exhaust gas composition. The deterministic, mechanically synchronized nature of conventional engines, the very feature that had seemed like an inherent advantage all along, meant that sensors and electronic controls could be wrapped around the system to manage emissions with increasing precision. The engine's fixed crankshaft relationship gave electronic systems a precise reference for timing every intervention. Free piston engines, with their probabilistic operation, their variable compression, their naturally varying cycle-to-cycle timing, were nearly impossible to manage with the emissions control tools available in the 1960s and 1970s. When the Clean Air Act of 1970 established real legal consequences for exceeding emissions limits, conventional engine manufacturers had a viable path forward through electronic control systems. Free piston engine developers had no comparable path. The very feature that made the engine brilliant, its self-optimizing physics-driven operation, made it incompatible with the legal framework being built around internal combustion engines in the world's largest market. Here's the thing about technology history that we tend to miss when we look backward. We focus on technical capability. Which technology worked better? Which one had higher efficiency? Which one had fewer failure modes? But the actual trajectory of technology adoption depends enormously on which technologies align with existing institutional frameworks, regulatory structures, manufacturing capabilities, and economic incentives. A technology that is technically superior but institutionally inconvenient will almost always lose to a technology that is technically adequate but institutionally compatible. The free piston engine was the wrong shape for the 20th century's institutions, not because of its physics, because of its paperwork, because of its supply chains, because of its regulatory incompatibility, because of the careers and factories and investment portfolios that were organized around something different. And yet, the story doesn't end with emissions regulations and gas turbines and institutional incompatibility, because the 20th century eventually ended, and the 21st brought with it a set of requirements, pressures, and technological capabilities that look remarkably like what Lungstrom had actually designed for, even if he didn't know it. The electric vehicle revolution that started seriously accelerating in the 2010s created a strange new problem that nobody had quite anticipated. Range anxiety. The genuine operational concern that your vehicle would exhaust its stored energy before reaching a destination or charging point. And the engineering solution that emerged, the range extender, turned out to need exactly what Lungstrom had built in 1928. A range extender is a small combustion engine carried aboard an electric vehicle not to drive the wheels directly, but to generate electricity that charges the battery or supplements the electric motor when grid charging isn't available. The requirements for such an engine are specific and demanding. It needs to be small and light, because you're already carrying a heavy battery pack. It needs to be highly efficient, because every percentage point of efficiency directly extends the vehicle's range. It needs to operate at a relatively constant load, because range extenders don't need to respond to throttle inputs the way conventional car engines do. They just need to run steadily and produce electricity. And ideally, it needs minimal maintenance, because nobody wants to bring their electric vehicle to a garage for valve adjustments every 30,000 miles. Run down that list of requirements against what Lungstrom built in 1928, and you'll notice something. Small and light. The free piston engine weighs 40% less than conventional engines of comparable output. Highly efficient. 50% thermal efficiency in 1928, before modern materials and electronic controls. Constant load operation. The free piston's self-optimizing character suits steady-state operation naturally. Minimal maintenance. 37 parts. No valves to adjust, no timing to set. Toyota unveiled a free piston engine linear generator at the Geneva Motor Show in 2014. The design took Lungstrom's fundamental concept and substituted a linear electric generator for the turbine. Instead of using the compressed air to spin a turbine, the moving pistons directly drove electromagnetic generators through linear magnetic interaction. No rotating parts at all. Toyota's claimed thermal efficiency for this design was 42%. Not quite the 50% Lungstrom achieved, but Toyota was meeting modern emission standards that Lungstrom never had to worry about. And this wasn't a research paper. This was a running prototype demonstrated at one of the world's most prominent automotive shows. The German Aerospace Center, the DLR, developed a competing free piston engine linear generator in 2016, specifically targeting range-extended electric vehicles. Their specifications read like a vindication of every advantage Lungstrom had claimed 90 years earlier. 35 kilowatts of electrical output. Package size comparable to a large suitcase. Weight of 65 kilograms. Thermal efficiency of 46%. Parts count under 50. The DLR's engineers weren't working from Lungstrom's patents. They were working from first principles, from physics, and they arrived at essentially the same architecture because the physics hadn't changed. Pistons bouncing freely, compressing and expanding gas, converting chemical energy to useful work without the mechanical overhead of cranks and camshafts, is still more efficient than the alternative. It was in 1928. It is today. Mainspring Energy, a Silicon Valley startup founded by former Tesla engineers, raised $150 million as of 2020 to commercialize what they call a linear generator for grid-scale power generation. Their device, which is functionally a refined free piston engine with a linear electromagnetic generator, claims 45% efficiency running on natural gas, biogas, or hydrogen. The maintenance interval they're targeting is 20,000 hours, roughly 10 times longer than comparable conventional generator sets. They're not pitching this as an automotive technology. They're pitching it as infrastructure, as the thing that provides reliable distributed electricity generation when solar and wind are unavailable. Lungstrom's self-optimizing, free-bouncing pistons reimagined as a component of the 21st century electrical grid. Even the world's most technologically conservative motorsport briefly brushed against free piston technology. In 2013, when the FIA was developing new engine regulations for Formula One's hybrid era, Ferrari's engineering team proposed allowing free piston range extender units aboard race cars. The idea was to pair a free piston generator with the MGUK kinetic energy recovery system to create a more efficient overall hybrid powertrain. Ferrari's simulations showed a free piston generator could be 30% lighter than conventional engine-based units while providing equivalent or greater electrical output. The proposal was rejected. Too radical. Too unfamiliar. too far outside the established framework of what a Formula One engine looks like. Here's what most people don't realize about that rejection. Formula One presents itself as the pinnacle of automotive engineering, the arena where the most advanced technologies are developed and proven. But the truth is that Formula One is also a commercial enterprise built around specific technical regulations that define what competition means in that sport. Changing the fundamental architecture of what competitors build doesn't just change the engineering. It potentially changes who wins, who loses, which manufacturers' existing investments become advantageous, and which become worthless. Institutional inertia operates in racing as powerfully as in production engineering. The fastest solution is not always the one that gets adopted. But let's step back from the specific applications and think about the broader pattern here, because this is where the story of the free piston engine stops being just an engineering curiosity and becomes something more universally instructive. Lungstrom was not an automotive engineer. This is crucial. He was a turbine specialist. He came to the problem of internal combustion with no investment in existing solutions, no career built around crankshaft design, no reputation staked on valve train optimization. He could look at the conventional engine and see it clearly, as a collection of engineering choices made under specific historical constraints, not as fundamental physical truths. And because he could see it that way, he could ask the question that insiders couldn't easily ask. Does all of this have to be here? Experts are genuinely expert at optimizing within established paradigms. They're often the worst people to ask about whether the paradigm itself is correct. Because the paradigm is the water they swim in. It's the assumed context for every problem they've ever solved. Asking an expert automotive engineer in 1928 whether the crankshaft was necessary was a bit like asking a fish whether water was necessary. The answer felt obvious. Of course it is. Everything we do assumes it's there. Lungstrom didn't know the crankshaft was necessary, so he tried without one. And it turned out it wasn't. The conventional engine's architecture, the thing every engineer in Detroit treated as bedrock, was actually a historical artifact, a set of solutions that had been developed under early constraints and then calcified into convention. The free piston engine demonstrated this with brutal clarity. You didn't need mechanical synchronization if you let physics do the synchronization. You didn't need a crankshaft if you didn't need rotational output. You didn't need valves if your pistons could serve as their own valves through port timing. This is where it gets really interesting. The same pattern, the genuinely superior innovation rejected by established institutions and eventually vindicated decades later, appears throughout engineering history with remarkable consistency. The gas turbine was dismissed by reciprocating engine manufacturers before wartime necessity forced its adoption. Solid-state electronics were dismissed by vacuum tube manufacturers as toys unsuitable for serious applications. The lithium-ion battery was considered a laboratory curiosity for a decade before consumer electronics created the market that proved its viability. In each case, the dismissal wasn't irrational, given the institutional context of the people doing the dismissing. It just looked irrational in retrospect, once the technology found its moment. The free piston engine's moment may finally, genuinely be arriving. Not because the physics got better. The physics was always there. But because the institutional context has shifted in ways that make the free piston's specific advantages, high efficiency, minimal parts, multi-fuel operation, self-optimizing compression, relevant in a way they haven't been since 1928. The push toward electrification creates demand for efficient range extenders. The push toward renewable energy creates demand for generators that can run on hydrogen or biogas without extensive retuning. The push toward lower maintenance infrastructure creates demand for prime movers with parts counts in the dozens rather than the hundreds. Burger Lungstrom died in 1979 at the age of 87. He lived long enough to see his free piston engine deployed in French submarines and industrial generators, to watch Sigma sell hundreds of GS-34 units to industrial customers across Europe, to see Pescara push the concept to 2,000 horsepower. But he didn't live to see Toyota demonstrated at Geneva. He didn't see the DLR's linear generator. He didn't see Mainspring Energy raise $150 million on a concept he had patented 90 years earlier. He never got the moment of complete vindication, the kind of vindication where the establishment that dismissed your work admits, clearly and on the record, that you were right, and they were wrong. That particular kind of vindication is, in the history of technology, almost vanishingly rare. The people who are eventually proven right usually aren't around to enjoy it. Or if they are, the vindication comes in a form so transformed by decades of subsequent development that the connection to the original work is obscured. When Toyota presents a linear generator at Geneva, they don't lead with, "This is based on work a Swedish engineer did in 1928 that Detroit dismissed as impractical nonsense." They present it as their own advanced engineering. Because in the immediate practical sense it is, the specific mechanical solutions, the electronic controls, the materials, the manufacturing processes, are all Toyota's. The physical principle underneath all of it is Lungstrom's. Now, you might be thinking, does the attribution even matter? If the technology is finally being developed and deployed, does it matter whether we remember who first demonstrated it? And I think it does, actually. Not for sentimental reasons, for practical ones. Because the story of the free piston engine isn't just a story about one engine. It's a case study in how engineering institutions evaluate unconventional ideas. And if we understand that case study clearly, we might make better decisions about the unconventional ideas being proposed right now. Think about what criteria Detroit used to reject Lungstrom's work. Not did it work, because it demonstrably did. Not was it efficient, because it demonstrably was. The criteria were, does it fit our existing manufacturing infrastructure? Does it sound like what our customers expect? Can our existing engineers understand and maintain it? Is it compatible with how we already do things? These are reasonable questions for a business to ask. They're not irrational. But they're also not the right questions if your actual goal is to build the most capable technology possible. They're the questions of an institution optimizing for its own continuity, not for technical excellence. And here's the uncomfortable part of this story. We like to tell it as a story about short-sighted corporations and a brilliant outsider. That framing is satisfying. It's clean. There are heroes and villains. But the reality is more complex and more useful. The engineers at General Motors who wrote that 1932 memo weren't stupid. They weren't even necessarily wrong about the specific concerns they raised. Control of free piston timing was genuinely difficult without electronic management systems. Consumer acceptance of unfamiliar engine sounds was a genuine market challenge. Retooling manufacturing infrastructure was genuinely expensive. Their mistake wasn't in identifying real challenges. Their mistake was in treating those challenges as permanent barriers rather than temporary engineering problems with engineering solutions. The challenges were real. The conclusion that the challenges couldn't be solved was wrong. And that distinction, between a genuine technical limitation and an institutional preference dressed up as a technical limitation, is something engineers and investors and technology evaluators get wrong repeatedly, in every era, in every industry. The free piston engine failed in 1928 to 1970, not because free pistons couldn't solve the control problem, but because the institutions evaluating the technology weren't willing to fund the work needed to solve it. Electronic controls that could manage probabilistic piston timing existed in principle long before they existed in practice. Making them practical required investment. The investment didn't come because the institutions didn't want it to. So the solution never arrived, and the absence of the solution was used to justify not making the investment. A circular logic that protected the established technology from serious competition. Now think about what this means for technology evaluation today. Right now, in engineering labs around the world, there are proposals for technologies that face similar objections. They work in principle but present control challenges. They're unfamiliar to existing consumers. They'd require significant manufacturing infrastructure changes. They can't meet current regulatory requirements with current development investment. How many of those technologies are being dismissed using the same logic that dismissed Lungstrom? How many would, with appropriate investment and development time, prove to be the free piston engines of the 21st century? Here's the thing about that question. You can't answer it with certainty from inside the institutional context that's doing the evaluating. This is the fundamental epistemological problem of disruptive technology. The institutions best positioned to evaluate and develop new technologies are the ones most invested in existing technologies. Their judgment is systematically biased towards solutions that are compatible with their existing infrastructure, capabilities, and market positions. This isn't corruption, it's just incentive structure. But the result is the same as if it were corruption. Superior technologies get held back, sometimes for decades, while adequate technologies continue to dominate because they're institutionally convenient. The free piston engine is a particularly pure example because the evidence is so clear in retrospect. 50% thermal efficiency in 1928. 37 parts. 80,000 hours of demonstrated operational life. Multi-fuel capability demonstrated on crude oil. These weren't marginal advantages. They weren't theoretical claims. They were demonstrated, measured, documented facts. And they were still not enough to overcome institutional inertia in the world's most powerful manufacturing economy. What should this tell us? It should tell us to be specifically suspicious of technical objections to unconventional technologies when those objections happen to align perfectly with the institutional interests of the objectors. When an established manufacturer says a competing technology won't work, ask whether they have the engineering resources to make it work if they chose to invest in it. Usually the answer is yes. Ask whether they have economic incentives to not make it work. Often the answer is also yes. The technical objection and the economic interest can coexist honestly in the same organization, without anyone being consciously deceptive. But the combination should make us cautious about taking the technical objection at face value. And look, this isn't to say all unconventional technologies deserve support. Most unconventional technologies fail because they have genuine, fundamental technical limitations. Not every outsider with an unusual idea is a Lungstrom. The vast majority of people who claim to have built a better engine than what exists haven't. The free piston engine is remarkable precisely because it actually worked. Because the test data was real. Because the physics supported the efficiency claims. Because Sigma built hundreds of production units that ran for decades. The bar for taking unconventional technology seriously has to be demonstrated performance, not just theoretical promise. But demonstrated performance should be enough. When you have an engine that has demonstrably achieved 50% thermal efficiency, demonstrably logged 50,000 hours without major maintenance, demonstrably run on crude oil, and you're dismissing it because it doesn't sound like what you're used to building, you've stopped doing engineering. You're doing institutional self-preservation and calling it engineering judgment. And that distinction matters. It mattered in 1928 in Detroit. It matters today wherever new technologies are being evaluated against established alternatives. The story of Burger Lungstrom and his free piston engine is ultimately a story about what questions we ask when we look at something new. Do we ask, what would it take to make this work? Or do we ask, why doesn't this fit what we already do? The first question leads to Toyota's 2014 Geneva prototype and Mainspring Energy's grid generators and the DLR's range extender. The second question leads to the 1932 General Motors memo. Both questions are being asked right now. About technologies that may look in 50 years the way Lungstrom's engine looks to us today. Either like an obvious missed opportunity, or like the seed of something that eventually changed everything. 90 years after Lungstrom walked into his Stockholm workshop and threw out the crankshaft, the principle he demonstrated is being rediscovered by some of the most sophisticated engineering organizations in the world. Not because the physics changed, because the questions finally changed. Because the institutional context shifted enough that asking, what would it take to make free pistons work in a modern application, became a question organizations were willing to fund, rather than dismiss. The engine that Detroit called impractical Swedish nonsense is now the design direction of choice for engineers trying to solve some of the 21st century's most important energy challenges. Burger Lungstrom didn't need vindication to be right. He was right in 1928. The test data said so. The physics said so. The Sigma production units that ran for 50,000 hours said so. History just took a while to catch up with the physics. And somewhere right now, there's another engineer asking the same kind of question Lungstrom asked. Not how do we optimize what exists, but does any of this need to exist at all? If you know of other forgotten technologies that deserved better than history gave them, drop them in the comments below. These stories matter. Not just as history, but as instruction for how we think about what comes next.